My dear students, hello. I welcome you all in our series of lectures on cybersecurity. Today, we are going to discuss about operating system security with special reference to Windows and Linux. We will discuss various security aspects of both through our comparison of both the operating systems. Let's start with it. It is possible that email and browser based viruses, trojans and worms are the source of the myth that Windows is attacked more often than Linux. Clearly, there are more desktop installations of Windows than Linux. It is certainly possible, if probable, that Windows desktop software is attacked more often because Windows dominates the desktop. But this leaves an important question unanswered. Do the attacks so often succeed on Windows because the attacks are so numerous or because there are inherent design flaws and poor design decisions in Windows? Many, if not most of the viruses, trojans, worms and other malware that infect Windows machines do so through vulnerabilities in Microsoft Outlook and Internet Explorer. To put the question another way, given the same type of desktop software on Linux, the most often used web browsers, email, word processors, etc., are there many security vulnerabilities on Linux as Windows? Let us now discuss Windows design. Viruses, trojans and other malware make it onto Windows desktop for a number of reasons familiar to Windows and foreign to Linux. Number 1. Windows has only recently evolved from a single user design to a multi-user model. Number 2. Windows is monolithic, not modular by design. Number 3. Windows depends too heavily on an RPC model. Let us discuss them one by one. Number 1. Windows has only recently evolved from a single user design to a multi-user model. It is said Linux is old technology. Ironically, one of the biggest problems with Windows is that it hasn't been able to escape its old legacy single user design. Windows has long been hampered by its origin as a single user system. Windows was originally designed to allow both users and applications free access to the entire system, which means anyone could tamper with a critical system program or file. It also means viruses, trojans and other malware could tamper with any critical system, program or file because Windows did not isolate users or applications from these sensitive areas of the operating system. Windows XP was the first version of Windows to reflect a serious effort to isolate users from the system, so that users each have their own private files and limited system privileges. This caused many legacy Windows applications to fail because they were used to being able to access and modify programs and files that only an administrator should be able to access. That is why Windows XP includes a compatibility mode, a mode that allows programs to operate as if they were running in the original insecure single user design. This is also why each new version of Windows threatens to break applications that ran on previous versions. As Microsoft is forced to hack Windows into behaving more like a multi-user system, the new restrictions break applications that are used to working without those restraints. Windows XP represented progress, but even Windows XP could not be justifiably referred to as a true multi-user system. For example, Windows XP supports what Microsoft calls fast user switching, which means that two or more people can log into a Windows XP system on a single PC at the same time. Here is the catch. This is only possible if and only if the PC is not set up to be part of a Windows network domain. That is because Microsoft networking was designed under the assumption that people who log into a network will do so from their own PC. Windows Server 2003 makes some progress towards true multi-user capabilities, but even Windows Server 2003 hasn't escaped all of the leftover single user security holes. That is why Windows Server 2003 has to turn off many browser capabilities such as ActiveX, scripting, etc. by default. Number 2, Windows is monolithic by design, not modular. A monolithic system is one where most features are integrated into a single unit. The antithesis of a monolithic system is one where features are separated out into distinct layers, each layer having limited access to the other layers. While some of the shortcomings of Windows are due to its ties to its original single user design, other shortcomings are the direct result of deliberate design decisions, such as its monolithic design, that is, integrating too many features into the core of the operating system. Microsoft made the Netscape browser irrelevant by integrating Internet Explorer so tightly into this operating system that it is almost impossible not to use Internet Explorer. Like it or not, you invoke Internet Explorer when you use the Windows Help System, Outlook, and many other Microsoft and third-party applications. Microsoft successfully makes competing products irrelevant by integrating more and more of the services they provide into its operating system. But this approach creates a monster of inextricably interdependent services. Interdependencies like these have two unfortunate cascading side effects. First, in a monolithic system, every flaw in a piece of that system is exposed through all of the services and applications that depend on that piece of the system. When Microsoft integrated Internet Explorer into the operating system, Microsoft created a system where any flaw in the Internet Explorer could expose your Windows desktop to risks that go far beyond what you do with your browser. A single flaw in the Internet Explorer is therefore exposed in countless other applications, many of which may use Internet Explorer in a way that is not obvious to the user, giving the user a false sense of security. This architectural model has far deeper implications that most people may find difficult to grasp. One being that a monolithic system tends to make security vulnerabilities more critical than they need to be. Finally, a monolithic system is unstable by nature. When you design a system that has too many interdependencies, you introduce numerous risks when you change one piece of the system. One change may and usually does have a cascading effect on all of the services and applications that depend on that piece of the system. This is why Windows users cringe at the thought of applying patches and updates. Updates that fix one part of the Windows often break other existing services and applications. The Windows XP Service Pack 2 already has a growing history of causing existing third-party applications to fail. This is the natural consequence of a monolithic system. Any changes to one part of the machine affect the whole machine and all of the applications that depend on the machine. Number 3, Windows depends too heavily on the RPC model. RPC stands for Remote Procedure Call. Simply put, an RPC is what happens when one program sends a message over a network to tell another program to do something. For example, one program can use an RPC to tell another program to calculate the average cost of tea in China and return the answer. The reason it is called a remote procedure call is because it does not matter if the other program is running on the same machine, another machine in the next cube or somewhere on the internet. RPCs are potential security risk because they are designed to let other computers somewhere on a network to tell your computer what to do. Whenever someone discovers a flaw in an RPC enabled program, there is the potential for someone with a network connected computer to exploit the flaw in order to tell your computer what to do. Unfortunately, Windows users cannot disable RPC because Windows depends upon it, even if your computer is not connected to a network. Many Windows services are simply designed that way. In some cases, you can block an RPC port at your firewall, but Windows often depends so heavily on RPC mechanisms for basic functions that this is not always possible. The most common way to exploit an RPC related vulnerability is to attack the service that uses RPC, not RPC itself. It is important to note that RPCs are not always necessary, which makes it all the more mysterious as to why Microsoft indiscriminately relies on them. Assume for a moment that you create a website using two servers. One server is a dedicated database server and the other server is a dedicated web server. In this case, it is necessary for the database server to use RPCs because the web server is on a separate machine and must be able to access the database server over the network connection. Even in this case, one should configure the database server to listen only to the web server and no other machine. If you run both the database server and the web server on the same machine, however, it is not only unnecessary for the database server to use RPCs, it is unwise to do so. The web server should be able to access the database server directly because the two are running on the same machine. There is no technical or logical reason to expose the database server to the network because it presents an unnecessary security risk. We raise the issue of database servers because the Slammer worm, one of the most profoundly dangerous worms ever to hit the internet, exploited one of the most inappropriate uses of RPC, like network communications ever implemented by Microsoft. Slammer infected so many systems so quickly that it practically brought the internet to a standstill. The Slammer worm caused havoc by exploiting two flaws in Microsoft SQL Server, a client server SQL database server. One flaw was a most improbable feature of Microsoft SQL Server, one that allows you to run more than one instance of the database server at a time on a single machine. Here is why it is improbable. If you are not familiar with database servers, picture it this way. Under normal conditions, it makes no sense to run multiple instances of a database server on a single machine because one instance is all that is needed, even if many different applications use it. One would be as likely to want to run two copies of Windows XP on a single machine at the same time as want to run multiple database servers on a single machine at the same time. One rarely runs multiple instances of a database server on purpose, except in high-end applications or for testing and development. Now, next is Linux design. According to Evans data, Linux developers survey 2004, 93% of Linux developers have experienced two or fewer incidents where a Linux machine was compromised. 87% had experienced only one such incident, and 78% have never had a cracker break into a Linux machine. In the few cases where intruders succeeded, the primary cause was inadequately configured security settings. More relevant to this discussion, however, is the fact that 92% of those surveyed have never experienced a virus, Trojan or other malware infection on Linux. Viruses, Trojans and other malware rarely, if ever, manage to infect Linux systems, in part because number 1, Linux is based on a long history of well fleshed out multi-user design. Number 2, Linux is most modular by design. Number 3, Linux does not depend upon RPC to function, and services are usually configured not to use RPC by default. And number 4, Linux servers are ideal for headless non-local administration. Let us discuss them one by one. Number 1, Linux is based on a long history of well fleshed out multi-user design. Linux does not have a history of being a single user system. Therefore, it has been designed from the ground up to isolate users from the applications, files and directories that affect the entire operating system. Each user is given a user directory where all of the user's data files and configuration files are stored. When a user runs an application such as a word processor, that word processor runs with the restricted privileges of the user. It can only write to the user's own home directory. It cannot write to a system file or even to another user's directory, unless the administrator explicitly gives the user permission to do so. Even more important, Linux provides almost all capabilities, such as the rendering of JPG images as modular libraries. As a result, when a word processor renders JPG images, the JPG rendering functions will run the same restricted privileges as the word processor itself. If there is a flaw in the JPG rendering routines, a malicious hacker can only exploit this flaw to gain the same privileges as the user, thus limiting the potential damage. This is the benefit of a modular system, and it follows more closely the spherical analogy of an ideally designed operating system. Given the default restrictions in the modular nature of Linux, it is nearly impossible to send an email to a Linux user that will infect the entire machine with a virus. It does not matter how poorly the email client is designed or how badly it may behave. It only has the privileges to infect or damage the user's own files. Linux browsers do not support inherently insecure objects such as ActiveX controls, but even if they did, a malicious ActiveX control would only run with the privileges of the user who is running the browser. Once again, the most damage it could do is infect or delete the user's own files. Even services such as web servers typically run as users with restricted privileges. In sharp contrast, Windows was originally designed to allow all users and applications to have administrator access to every file on the system. Windows has only gradually been reworked to isolate users and what they do from the rest of the system. Windows Server 2003 is close to achieving this goal, but the methodology Microsoft has employed to create this barrier between user and system is still largely composed of constantly changing hacks to the existing design, rather than a fundamental redesign with a multi-user capability and security as the foundational concept behind the system. Number 2, Linux is modular by design, not monolithic. Linux is, for the most part, a modularly designed operating system from the kernel to the applications. Almost nothing in Linux is inextricably intertwined with anything else. There is no single browser engine used by help systems or email programs. Indeed, it is easy to configure most email programs to use a built-in browser engine to render HTML messages or launch any browser you wish to view HTML documents or jump to links included in an email message. Therefore, a flaw in one browser engine does not necessarily present a danger to any other application on the system, because few, if any, other applications besides the browser itself must depend on a single browser engine. Not everything in Linux is modular. The two most popular graphical desktops, KDE and GNOME, are somewhat monolithic by design, at least enough so that an update to one part of GNOME or KDE can potentially break other parts of GNOME or KDE. Neither GNOME nor KDE are so monolithic, however, as to require you to use GNOME or KDE specific applications. You can run GNOME applications or any other applications under KDE, and you can run KDE or any other applications under GNOME. The Linux kernel supports modular drivers, but it is essentially a monolithic kernel where services in the kernel are interdependent. Any adverse impact of this monolithic approach is minimized by the fact that the Linux kernel is designed to be as minimal a part of the system as possible. Linux follows the philosophy that whenever a task can be done outside the kernel, it must be done outside the kernel. This means that almost every useful feature in Linux is a feature that does not have access to the vulnerable parts of a Linux system. In contrast, bugs in graphic card drivers are a common cause of the Windows blue screen of death. That is because Windows integrates graphics into the kernel, where a bug can cause a system failure. With only a few proprietary exceptions such as third-party NVIDIA graphic drivers, Linux forces all graphic drivers to run outside the kernel. A bug in a graphic driver may cause the graphical desktop to fail, but not cause the entire system to fail. If this happens, one simply restarts the graphical desktop. One does not need to reboot the computer. Number 3, Linux is not constrained by an RPC model. As discussed earlier, RPC stands for remote procedure call. Simply put, RPC allows one program to tell another program to do something even if that other program resides on another computer. Most Linux distributions install programs with network access turned off by default. For example, the MySQL SQL database server is usually installed such that it does not listen to the network for instructions. If you build a website using Apache and MySQL on the name server machine, then Apache will interact with the MySQL without MySQL having to listen to the network. Contrast this to SQL Server, which listens to the network whether or not it is necessary to do so. If you want MySQL to listen to the network, you must turn on that feature manually and then explicitly defines the users and machines allowed to access MySQL. Even when Linux applications use the network by default, they are most often configured to respond only to the local machine and ignore any requests from other machines on the network. Unlike Windows Server 2003, you can disable virtually all network related RPC services on a Linux machine and still have a perfectly functional desktop. Next is realistic security and severity metrics. One needs to examine many metrics in order to evaluate properly the risks involved in adopting one operating system over another for any given task. Metrics are sometimes cumulative, at other times they offset each other. There are 3 very important metrics represented as risk factors, which have a profound effect on one another. The combination of the 3 can have a dramatic impact on the overall severity of a security flaw. These 3 risk factors are damage potential, exploitation potential, and exposure potential. Damage potential of any given discovered security vulnerability is the measurement of the potential harm done. A vulnerability that exposes all your administrator passwords has a high damage potential. A flaw that makes your screen flicker would have a much lower damage potential raised only if that particular damage is difficult to repair. Exploitation potential describes how easy or difficult it is to exploit the vulnerability. Does it require expert programming skills to exploit this flaw, or can almost anyone with rudimentary computer experience use it for the mischief? Exposure potential describes the amount of access necessary to exploit a given vulnerability. If any hotshot hacker on the internet can exploit a flaw on a server you have protected by a firewall, that flaw has a very high exposure potential. If it is only possible to exploit the flaw if you are an employee within the company with a valid login ID using a computer inside the company building, the exposure potential of that flaw is significantly less severe. One or more of these risk factors can have a profound effect on the overall severity of a security hole. So, with this, our today's lecture on Windows and Linux security is over. We have learned about various factors that affect the security in both Windows and Linux operating system. We also learned about various security metrics that are needed to evaluate the risks that can arise in an operating system. I hope you have understood today's lecture, and the next class we will learn about various security issues. Till then, goodbye, have a nice day.